Hey, welcome. Today we're going to be talking through what are radians, what are phases of oscillating waves, and phase shifts between waves. So that's a mouthful. There's a lot to that question, and we're going to get to it. I want to address some things first, though. First off, I do want to talk about what a radian is. Now, you may have seen this in math class or other classes. I want you to take a look at the animation on the left. You can see a radius being traced out in just a moment. So that's our radius right there in red. If that becomes an arc length, then the angle that is traced out from the beginning and the end of that arc length is equal to 1 radian. So conceptually, that's what a radian is. And if you continue that, if you say 180 degrees, what would that be equal to? Well, it turns out that that is equal to pi radians. And if that's true, then a 360 degree angle measurement would be equal to 2 pi radians all the way around. So that's just a quick reminder of what we mean by radians. We will be using radians today, so it's assumed that you know something about them. Now, let's understand some other things about the actual question that I had asked you. Phases of oscillating waves. We'll get to what phases are, and we'll get to what phase shifts means. But I just want to say at the outset, what is an oscillating wave? Well, an oscillating wave is one that's going to repeat over and over and over again. And so sometimes they're also called periodic waves. You could say that's contrasted with a pulse wave. That is just one wave pulse, one full wave that is sent along its way, like down a slinky. Alright, so let's go ahead and talk about these degrees down here that you see. So if you were going to start your measurement from the positive x-axis over here, and you do a measurement around here, we said that this would be pi radians around. That's 180 degrees. And a full circle would be 360 degrees or 2 pi radians. And if that makes sense, then you could say, well, half of that pi radians or 180 degrees would be 90 degrees right here, or 1/2 pi radians around the circle down below here. This would be at the 270 degree mark, or 3/2 or 1.5 pi radians. Let's go ahead and continue. So while we're talking about radians, I would be remiss if I didn't just mention this, how to convert between degrees into radians and radians into degrees. So if you know the equivalency here, you know 360 degrees is equal to 2 pi radians, then you could say, well, it's just like any dimensional analysis problem, and you can do one problem this way, or you can do another problem the other direction, meaning converting from radians into degrees right here. This would be another example we could look at. All right, let's continue and think through phases of the moon. So this is another thing that you may be familiar with, or maybe not, but it's actually really useful and important to think about. So there are phases of the moon. You may have heard some of these terms before, like a new moon, a full moon, but these phases are just different times of the month where you'll see different amounts of the moon. So you can almost think of it as the Earth is in the center and you measure an angle around here. So I want you to think about phases as repeating stages of a continuous cycle, because we're going to talk about phases in terms of a repeating wave cycle. Alright, so let's continue and we will take a look at phases of waves that are out of phase. So what does it mean to think of waves that are out of phase? Alright, so if we were to plot in real time the cosine of theta and the sine of theta, we would get these graphs. In real time, they are offset by each other. So in other words, they are basically the exact same graphs, except they are shifted over by a certain amount. In other words, the crest of one wave is not hitting the highest amplitude at the same time as the crest of another wave. So like right now, the red wave, the sine wave, is cresting, and the blue wave was not cresting at the same time. If they were shifted over so that they were on top of each other, they would be completely on top of each other, is another way to think about that. So to say they're out of phase means one wave is just shifted over from another wave. Alright, so let's continue with that and remind ourselves of what do we mean by a wavelength. So a wavelength, the easiest way to measure a wavelength is from one crest to one crest, or one trough to the next trough. Sometimes students get confused if they say, well, it's from the middle axis line to the middle axis line. That's actually not true. This would be 1/2 of a wavelength right here. If you're going to use the middle axis line, you got to think, well, the wave is going down at this point, it's going up at this point when it crosses the middle axis. It not only has to cross the same point, but it has to be going in the same direction. So here the wave is going down, here it's going up. The next time it's going down, then it crosses the middle axis line is over here. So if you want to use the middle axis line, you would say this is the distance between here and here would be our wavelength. So just want to throw that out there, as that's a common misconception that students will make. To make it easy, just measure the wavelength from one crest to one crest, or one trough to one trough. That's what we mean by a wavelength. Building on that, I do want to ask you, how much of a phase difference is there between points A and points B in terms of radians? So phase difference, meaning at different points or stages of this. So at this point you could say that they're both crossing the middle axis line and both waves are heading down. So you've got a complete cycle between A and B. So there is enough time for a complete cycle to happen. And as a result, you could say, well, in terms of radians, what's a complete circle or a complete cycle if you're going to plot it over time? Well, that would be 2 pi radians, right? So let's continue. How much of a phase difference is there between points A and C in terms of radians? Well, you haven't had enough time for a complete cycle to happen. How much of a cycle have you had? Well, you've had half of a cycle happen, you could say. And what that means then, in terms of radians, 1/2 of a circle or 1/2 of a cycle, if you're going to plot this position with time, would be 1 pi radian, right? So that's the difference between A and C in terms of their phase difference. And how much of a phase difference is there between points A and D in terms of radians? All right, this is where it's helpful. It's a little harder to see A and D, like the difference. Well, what difference would that be? The way I think about it is I think, all right, well, the whole thing is 2 pi radians. So this distance right here would be half of 2 pi. Well, that would be 1 pi radians. And this distance right here is half of 1. Well, half of 1 would be 0.5, or a half pi radian is what we're looking at for the offset between A and D right here in terms of their phase difference. And that's looking at the differences in one wave. Now what we're going to do is build on that idea and look at differences between multiple waves, 2 waves. So if I plot this graph right here as like my standard wave of sine of x right here, I've written in my amplitude of -1 and +1 over here. What we're going to say is if I were to plot 2 waves right here, you can see that they are offset by pi radians right here. And that would give us a phase shift of pi radians right here. That's what these 2 waves plotted at the same time would look like. Well, think about what if I were to offset it by 0.5 radians. What would it look like? It would look something like this. This is going to be harder to spot visually. It's harder to get used to looking at an offset of half pi radians, but I'm going to show you how to think through this. Lastly, I do want to say is if you're offset by 2 pi radians, you actually would just see both waves on top of each other. Why? Well, if you took one wave and you shifted it over, and it's a continuous or oscillating wave, you shifted it over by 1 full wavelength, it would just match up with the other wave that you're comparing it to. So there would be no difference visually speaking. Alright, so let's test our understanding. Let's see or quiz ourselves and see if you can understand what's happening here. At one point on the x-axis, how many degrees or radians are the 2 waves off by? So that's going to be our strategy here. So think about it. If you look at, say, this point in the x-axis, you could say, well, I know that this wave right here is at one extreme. This wave is at another extreme. So they are off by half a cycle, basically, is one way to think about it. And half a cycle would be pi radians, or 180 degrees phase shifted one from another. You could also say the same thing is happening here. They look like they're at the same point, but one is going down, one is going up. That's still off by half a cycle. Half a cycle would be pi radians, or 180 degrees. Alright, let's try another problem here. This is going to be a lot tougher to think through to come up with the correct answer, but my advice is just look at one point on the x-axis and see if you can figure out how much it is shifted over by. So compare the red and the blue waves at one point on the x-axis. So let's just pick this point right here. We know that the red wave is just going to be at its equilibrium position, and at that point right here, the blue wave is at its maximum amplitude, its maximum displacement from the middle. So if you think about it, how much of a cycle would it take to go for the red wave to match that, to go from its equilibrium position to its maximum amplitude position? Well, that would be, what part of a wave cycle would this be? Well, that's something we can figure out, right? Because if we say, well, it would take this whole thing to be one cycle, this thing right here would be 1/2 of a cycle, and then this thing right here would be 1/4 of a full cycle. All right? Well, if I know a full cycle is 2 pi radians, this distance right here, and I know 1/2 of a cycle, this distance right here is pi radians, then I know going from this point to this point, the angle that it would take for us to get there would be 1/2 of a radian, you could say. So that's going to be our phase shift of 1/2 of a radian. That last example is not very easy to get. I think you might want to re-listen to that if that was a little tough for you. It takes a little while for these concepts to sink in. Think of one full cycle as being 2 pi radians. 1/2 of that would be pi radians, so 1/2 of a cycle. And then if we have something like that, that would be 1/4 of the whole thing. 1/4 of the whole thing, or 1/2 of 1 pi radian, would be this distance right here, and that's what they are offset by, because you can see this red wave is at the equilibrium position, this blue wave is at the maximum displacement or the maximum amplitude, and that is the distance that we need to go in terms of the cycle, which would be 1/2 pi radians difference between the two. So hopefully this has been helpful. I'm going to be covering all of the major ideas in a physics course, as well as additional ideas kind of like this. We're going to be addressing the question of how do you communicate with a cell phone, and that's what we're building up to. So I hope you all have a great day. Take care.